So, systems. What if I have more than one independent variable? So here is an example of what I mean by such a system. I have two different functions, x of t and y of t. They not only depend on t, but they depend on each other as well. So my function g1 is some function which is linear in t and x and y. So we have to be linear in all of our variables. Gesundheit. So something like this. Now, CI, C1, C2 could be C1 of t or C2 of t. But they can't have x's or y's in the ones that don't go with the x or y variable. And same thing with G2. Like that. You know what? I think I'm going to call them C again, but instead of C1 and C2, we'll call them C3 and C4. If it looks like this, that is a linear system of equations. If we've got something that's got x times y in it, then it's not linear. If we've got an x squared, if we've got a y squared, this is the same setup as what we were talking about the definition for linear differential equation back in chapter 3. So what's something that behaves like this? Well, there are lots of different examples, and my goal is to try and figure out how to get a model that looks like this. What situations arise that gives me this sort of thing? Well, here's one that's absolutely crazy. Ready? Radioactive uranium. Uranium-238. Uranium-238 decays. Eventually, at the very end of this decay chain is lead. So if you start with a kilogram of uranium, eventually you end up with lead and nothing else. But what happens is we emit alpha particles. Alpha particles are charged electrons, charged neutrons. I don't remember which. No, alpha particles are helium nuclei. They are 2 protons and 2 neutrons. They get spit out. Beta particles are charged electrons. They get spit out, and our atomic mass doesn't change, but our overarching element changes. So this is what happens to uranium. Now, we could pick any radioactive element, anywhere in this chain. Things like radium, or radon, or polonium, or thorium. And we could look at what happens. But let's just look at the very top here. These first 3. Uranium decays into thorium. Thorium decays into Pa. Palladium? Chemistry was a long time ago, people. I'm just going to call it Pa. But what happens to my quantity of uranium as time goes on. It starts to go away. What happens to my quantity of thorium then? Goes up. But at the same time, some of those thorium atoms are decaying into this, right? So it's not just going up, it's also going down. There's some balancing act here. And then the amount of palladium is going up. I was only looking at these three, so I can say, oh, this is going down. It's turning into this, so that should be going up a little bit based on how much uranium I have, but it should be going down based on how much thorium turns into this. So I've got three different behaviors here. By the way, uranium-238 is fairly stable. Its half-life is 4.5 times 10 to the 9th years. That's annum. Is years up there. 10 to the 9th. That's billions of years. Thorium, on the other hand, its half-life is 24 days. It decays fairly quickly. Some of these are really quick. Polonium-218 is a half-life of 3 minutes. So here's another one that's even crazier. Polonium-214 has a half-life of milliseconds. You really don't get to be polonium-214 for very long at all. But what that means is that I can create a sequence of changes. Let's take a look at potassium. Page 111, potassium. Interestingly enough, the most common place for potassium, come on, athletes, where's the most common place for potassium? Bananas. Yeah, but that means shipments of bananas and shipments of potatoes are radioactive. Do you know one of the most amusing smuggling operations in the world was to smuggle watches in shipments of bananas? Analog watches with glowing hands. The glow in the dark is radioactive tritium. The radiation wouldn't show up on the background because of the bananas. So they hid glowing watches in bananas. I wish I was making this crap up. Oh, did somebody notice the weight difference? Yeah. Watches are heavier than bananas. So, potassium-40 is radioactive. Over time, it decays two different ways. It can decay into calcium, or it can decay into argon. Now, here's the funny part to me in this problem. I teach this problem. I then go over to that classroom across the hall to observe a thermo class. You know what they're studying? This exact problem. And I'm sitting in the back of the room giggling like hell because they're doing the equations we're going to come up with. So I say to myself, the amount of calcium is going to change. The amount of calcium is going to change. And it's going to change because potassium is going to turn into it, right? Potassium is going to turn into calcium. Potassium is K, so this is some number times the amount of potassium. The more potassium I have, the more it decays. The amount of argon is going to change. And it's proportional to the amount of potassium as well. But those might not be the same numbers. So let's call this one lambda 1 and this one lambda 2. So what's my change in potassium? I start with some potassium. I mashed up all my bananas and got it out. I mashed the potatoes, got it all out. Some of it's going to turn into calcium, and some of it's going to turn into argon. What about the rest? The rest just stays there, right? Only so much of it decays at a time. So I don't just vaporize my potassium. So whatever went into becoming calcium and argon has to come from the potassium I started with. So as the amount of calcium goes up and the amount of argon goes up, the amount of potassium has to go down. You know the best part about this? This third equation right here, this is separable. It only contains one variable, K and T. These contain multiple variables, but this one only, I can solve this one explicitly and get a function for K, can't I? If I was starting with a kilogram of potassium, I could work that out. If I say I start with a kilogram of potassium, no argon and no calcium, I can tell you what's going on for all three things over time, first by solving this equation and then substituting it in there to solve for those, right? That's gross. It's not short. But I've created a model just from the setting. And by the way, the textbook actually gives me these two numbers, lambda 1 and lambda 2, and says, if you know that, how long is it going to take for half your potassium to disappear? Well, I have to work out the equations. Let's at least do part of this. Let's start here. That one's separable. Let's solve that sucker. Separate and integrate. I get rid of the ln. I get K equals e to the negative lambda 1 plus lambda 2. Notice I factored out the other minus sign. T, there should be a plus C here, right? Wait a minute, I've already used C. C is something else. We'll call this plus D. I have C, I have A. If that's being added in the exponent, it's the same as multiplying out front. So I'm going to put a B here. If I knew I was starting with 1 kilogram, then I would know the value of B, wouldn't I? Right? Because I'd put in T equals 0, I'd get e to the 0. E to the 0 is just 1, so B has to be equal to 1 kilogram. But now I have an expression for K, which I can put into those two expressions up there. K equals 1 e to the minus lambda 1 plus lambda 2 t. dc dt is equal to lambda 1 k. I explicitly have an equation for k, which means I can just integrate, solve for c. What's C? When I said the problem, I said we started with potassium, but we didn't have any calcium and we didn't have any argon. So I know that C of 0 is 0. I know the same way that A of 0 is 0. But you can solve for C. You can solve for A the same way. Please do so. Tell me what you get. E to the number t. What's the antiderivative for e to the number t? The integral of e to the 3t is. So the integral of e to the number t is 1 over number, right? E to the number t. So I'm going to get lambda 1 over minus parentheses lambda 1 plus lambda 2 e to the negative lambda 1 plus lambda 2 t plus some new constant. And using my initial condition, I can solve for this number. So that means that b, as I move this constant to the other side, lambda 1 over lambda 1 plus lambda 2. Put that back in here. And I get C equals lambda 1 negative lambda 1 plus lambda 2 e to the negative number plus lambda 1 over lambda 1 plus lambda 2. Or if you'd rather, you can factor out this and get 1 minus e to the negative lambda 1 plus lambda 2t. That's nasty looking. Now, here's a question for you. What's the difference between the equations we just did for calcium, the equation for argon. The A of T. So the only difference is here, and that means the only difference is going to be this lambda 1 out front. All the way through is going to be a lambda 2. So following the exact same process, I get that A of T is lambda 2 over lambda 1 plus lambda 2, 1 minus e to the negative stuff. Boop. Now this actually turns out to be computable. If I observe some potassium 40, and I look at what it decays into, I can go down to the chemistry lab, down the hall or downstairs, and go to the lab, and I can say, run this experiment for me. Take some radioactive potassium and watch it decay, and then sort the calcium from the argon. Well, what kind of an element is argon? It's a gas. So the argon will float away, and I'll catch it in a funnel, right? And what I'll be left with solid is calcium and potassium, right? And I can say, well, how much argon did I get? And if I know how much argon I got, I know how much calcium I got. And I can figure out what these numbers, lambda 1 and lambda 2, are by running an experiment. And it turns out that we can actually work these out. That I get these numbers. So I have a question for you. If I let my potassium go, and I'm just going to let it all decay, it's all going to turn into argon and calcium. Which will I have more of? C or A? Because that one is bigger than this one. The bottoms are the same. And as time goes on, this is e to the negative. That's a transient term. That goes to 0. So over time, I will end up with more calcium than argon. And we actually can verify this experimentally. It'll be 89% calcium and 11% argon based on these numbers. Now, since argon is a gas, I need to take into account the fact that gases expand, right? And if I do this in a closed environment, I have a problem. But if I want to make argon, this is a way to do it. Argon's a stable element. It's a useful element. We put it in headlights. Whew. Questions? Talk to me. I can take situations we've already been in and modify them just a little to end up with this sort of a system of equations. Do you remember our salt tanks? We had a tank. We had fluid coming in and fluid coming out, right? What if there's another tank? But wait, there's more. There are two hoses. Stuff goes into tank A, and then tank A and B go back and forth with each other, and then stuff comes out of tank B. So I still have fluid in and fluid out, but I also have some mixing going on. Yes? A feedback loop like this. Okay, hang on a second. Let me step away from tanks. As soon as I said the word feedback, my brain went to other situations. If I say feedback, what's the thing you think of most commonly? What comes to mind when you hear the phrase feedback? Like from a microphone, which is a feedback in an electric circuit, right? The microphone is connected to a speaker. And what's amplified, what goes into the mic gets amplified, pushed to the speaker and goes out. And if that sound gets picked up by the microphone, it does it again and again and again. And off goes the feedback, right? Distortion on an electric instrument is exactly this sort of system. Feedback in electric systems. My favorite electric system runs my body. Nerves are all about feedback behavior. I push on my fingertip with something, and certain nerves are reacting. They're sending electrical systems into my brain. By the time the electricity leaves my finger and goes to my brain, I've burnt myself. That's why we have reflexes to short circuit that procedure. But that feedback behavior is what's happening. Question: how many of you right now are aware of the weight of your shirt on your shoulders? You weren't until I said something about it, were you? You weren't until I said something, because your body got used to it. And you got used to it to the point that the feedback shut off. The transient behavior turned off.
Go off that. So like when we first put a shirt on in the morning, like
You feel it.
yeah. So like after time, since that's like a more routine process. So after time, we just don't
Yes,
feel it.
your brain stops thinking about that signal. Just like you're not thinking about the fact that you're standing on your feet and the ground is pushing up on you until your feet start to hurt, right? You ignore it. The one that used to drive me crazy because it was an old Peanuts cartoon. You're not really aware of the fact that your tongue is in your mouth right now. Just how dare you? Isn't it? I don't see my glasses until I pay attention to them. I'm just used to being able to see you all. I don't feel them on my nose, even though I know they're there, or on my ears. You put your earbuds in. Do you pay attention to the fact they're pushing on your ear? Feedback loops. We're in them all the time. Anybody own a cat or owned by a cat? Cat box. Same damn thing, right? When you come home, you recognize it. After you've been home 10 minutes, I don't notice the cat box. Okay, let's go back in, oh God, chapter 3, we did the tank model with just one, right? So let's think about this. I have a tank that holds 50 gallons. Tank A has 25 pounds of salt. Tank B has none. X1 of T is pounds of salt in tank A at time T. And X2 is going to be the same thing for tank B. Now, in order for me to get this to a set of differential equations, I need to know stuff about what's going on in that picture. I need to know about what's going in on the left, what's going back and forth between tanks A and B, and what's coming out on the right. So I'm going to go back up to that picture and I'm going to add some numbers. Actually, I'll redraw the picture. It's easier. The fluid going in is 2 pounds of salt per gallon and is going in at 3 gallons per minute. The amount of fluid coming out of tank A is 4 gallons per minute. The amount of fluid coming out of tank B on the right is 3 gallons a minute, but some other fluid is coming out of tank B on the left at 1 gallon per minute. So please notice, all the tanks contain the same amount of water, liquid, at any given time. I'm adding 4 to tank A and 4 to tank B. And I'm taking 4 out of tank B. So 4 in, 4 in, 4 out. Everything balances, right? I'm good with this. Okay, back to the way I used to set this up. How do I figure out dx dt for tank A? Yep. So let's figure out how much salt is going in. How much salt is going in every minute? Because it's 2 pounds per gallon times 3 gallons per minute. That's pounds per minute, exactly like you said, Mia. So no, that's exactly the right number. How much salt is coming out of tank A? Ah, well, that's a good question now here. Remember, there was salt in tank A to start, right? Stuff's coming in and then it's being mixed. So it depends on how much salt is in tank A at the time, right? At time 0, there was 25. Plus something. Maybe. But why don't we just leave it as a straightforward idea? I have however much salt is in tank A in pounds divided by the 50 gallons of liquid. Because there's 50 gallons in each tank. And it's coming out, that's pounds and gallons. And then I need gallons per minute, right? Pounds, gallons, gallons per minute. How much is coming out? Ah, 4 gallons per minute. So that's going to be, I can simplify that if you want, write it as 2 over 25, but I'm okay. 6 minus 4x1 over 50. But we didn't quite get everything. Shaking your head, Mia, what did I miss? There's still more salt coming back into tank A. It's coming in from whatever's in tank B, right? And since I know salt is eventually going to reach tank B, some of that's going to get pushed back to A. So I need to add more salt back here. So I need to change this. And I need to say this is 6 plus something minus 4x1 over 50. What's the something? Because it's 1 gallon per minute, right? Perfect. So now you'll notice that I have dx1 dt equals, I'm going to write it in order, negative 4 over 50 x1 plus 1 over 50 x2 plus 6. And that's a function of x1 and x2, which are linear. In this case, they have constant coefficients, which is really nice. And then my f1 of t is also a constant. But that's only tank A. What about tank B? I got to scroll back up to my picture so I can see what's going on. Scroll, 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 scroll. Here's tank B. How much salt is going into tank B? I'm going to do salt in minus salt out for tank B. Because that's the stuff that's coming out of tank A, and the only thing that's going into tank B is coming from tank A. Great. So this thing right here, this term, that's the stuff that's going into tank B. So it'll be positive instead of negative. 4 over 50 x1. What about the salt coming out of tank B? There's no x3 because there's no third tank, right? But the stuff that's coming out here is still based on the salt in tank 2, right? Tank B. So that's also x2 over 50. And it's 3. But it's 3 of them going out this way, and it's 1 of them going out that way. So it's still 4 over 50 x2. It's just going in 2 different directions. And I'm actually going to write it the way you said it, Cody. I'm going to think of it as the salt out being 1 over 50 x2 and 3 over 50 x2. And then I can combine them to write one equation. And now I have 2 equations, which are both linear in x1 and x2 and t. And if I can figure out how to solve this, you can eventually tell me what will happen in the long term for the amount of salt in each tank. By the way, There's absolutely no reason to stop at 2 tanks. There's 3. Here's 3. We can have as many tanks hooked up as you want. Questions? If I can do the mixing problem for 1 tank, I can do the mixing problem for 2 tanks. When we started our discussion back in August, I was talking about mice in a field, right? About the number of mice in a field at any given time. And we looked at our growth model for mice in a field. All right. Let's consider what happens if I have 2 different species in that field. Owls eat mice. So I have number of owls and number of mice. I have foxes and rabbits. I have, I don't know, lions and deer. Hopefully that's not in my backyard. Sure, birds and worms. But I have, what's going to happen? Birds and worms. What's going to happen? Well, if there are only a few birds, I should have a lot of worms. But when there's a lot of food, what happens to the number of birds? It should increase. But then the number of birds will go up and they'll eat more worms, right? That means the number of worms will go down. So these 2 populations should kind of follow each other in some sense. If I have no prey, what if I ran out of worms? What would I expect to happen to my predators? They'll go. They'll slowly decrease, right? They'll age out. Maybe they'll eat each other. I don't know. But if there are prey, then somehow both of those things interacting should work with each other. So I can think of my dx dt as, well, if there were only predators, it should go down. But if there are some prey, then depending on how many there are between the 2, the ratio, the product, some of the predators eat some of the prey, and that makes them grow up, right? So that I can add something. On the other hand, what if there were no predators? If there were no birds, what would happen to my worms? I get worms everywhere. So I would expect some number y. But if there are predators, they should eat some of the worms, right? And again, it'll be the ratio, the product somehow, and that would cause my number of worms to go down. You'll notice I can factor these. I can write this as x times a plus by, and I write this as y times, I'll write it as a linear equation the same way, d minus cx. Now, the interesting part is this model was studied by a couple of Russian mathematicians. This is called a Lotka-Volterra model. And the solutions to Lotka-Volterra models are not elementary functions. They're not sines and cosines and exponentials and products. They're weird-ass functions. They're very hard to actually work out in terms of nice behavior. By the way, Problem number 11 in the text just throws some numbers on this. If I throw some numbers on this, I can graph this. Crap, I left that downstairs. Slopes. Remember this, the graphing application for the differential equations? There's a whole section titled systems. Tap. I can put in my equation. Now this has three. Let's change which system we're using. Nope, wrong button. Settings. Where's my model choice? I want to delete this model. Screw it, we'll just leave it empty for the moment. dx dt is negative 0.1 x plus 0.02 xy. Oh, wait a minute, these are, yes, xy. And we're going to start with x of 0 being 6. And then y prime, we're going to go with 0.2y minus 0.025 xy. We'll start with y of 0, also being 6. Where's my frame setting? Maximum t, we're going to go all the way out to 50. Maximum x values, we're only going to go up to 12. Take a look at that. The red equation is my predator equation. The green equation is my prey equation. Look at what's happening. We start out with more prey than predators. And then our predator numbers grow and they start to eat more of the prey. The number of prey bottoms out, and we can't support the big population of predators, so they start to die off. And all of a sudden, we see a cycle. There's that exact same change happening again. We're going to get a periodic behavior. It's just not a nice set of trig functions, unfortunately. Where have I seen like this before? Same idea for a model. We can think of competition models. If they're competing for resources instead of competing for each other. One of the most commonly used models in this type is called a SIR model. SIR, problem number 17. Stop share. A communicable disease is spread throughout a small community by contact between infected individuals and people who are susceptible, S. People who are infected, I. And people who are recovered and now immune. A SIR model is a system of differential equations, but there are 3 equations because it's the number of susceptible times the number of immune that governs the change in susceptible. It's the number of immune and the number of susceptible and immune that give me the change in infected. And the number of recovered is the number of people who were infected and aren't anymore. There's an adapted version of this model where people can become susceptible again after a period of time. You had the disease, you recovered, you were immune for a while, and now you can be sick again because the disease mutated. You know, like the flu. It's November, get your flu shot. It's exactly what this model is about. People, I taught this course 2 years ago, right after COVID. And when I wrote that model down, people went, "Mother." That's what they've been doing at the CDC for all this time. They've been trying to figure out the right coefficients to get this model to figure out what's going to happen. They do it with the flu. They do it with RSV. They do it with COVID. They do it with any susceptible disease. Systems of differential equations are vitally important. Tomorrow, we'll talk about how to actually solve them. I will see you all then. No, that's not tomorrow. That's Friday for you guys, right? I don't see you guys tomorrow. I'll see you Friday. See the calc people tomorrow.